Hello, and welcome to the third and final class in this Computation with Structured Data video course. This one is Structuring Data Using Tabular. The learning objective for this class is to introduce you to the Wolfram language function tabular, which is a size and computation efficient way to work with rectangular data. We'll talk about this a little bit more later, but you may remember that associations and data sets can have more complex nested structures. With tabular, it's just rectangular, and we can take advantage of that fact in order to make it more size and computation efficient. After you finish this class, you'll be able to build tabular objects from scratch, as well as create them from your own existing data. You'll be able to convert between tabular and other data formats in Wolfram language. We'll show you how to perform operations on the columns of tabular objects, and because they are rectangular, you can really freely think about them as columns. And we'll finally do a little example of how to analyze and visualize tabular data. All right, well, let's get started with tabular. The idea is that lists and associations of data sets, like I mentioned before, these allow you to be really, really arbitrary in the way that you store your data. You can have, crazy, ragged and jagged nested structures. You can have all sorts of different mixes of types. But in many cases, your data really is just rectangular, and you don't really need to take advantage of the kind of insane flexibility offered by these previously discussed methods of data structuring. In these cases, you can take advantage of the efficiency of a tabular object because it has this nice, simple row and column layout. Here's an example of a tabular. It's got rows, it's got columns, and notice here that typically when you have some sort of like measurement, which is a row, when you have a column, all the things in that column are of the same type, and tabular takes advantage of this in order to be more efficient. So see, these are all strings, these are all numbers, in this case integers, and these are all dates. And you can also see here that tabular nicely supports missing objects, so you don't have to worry if something is missing in your columns or rows. So you can really think about tabular as a more efficient form of data set with the limitation that it only works on rectangular lists of associations. It does work on rectangular lists as well, but kind of the primary way to do it with named columns is with rectangular lists of associations, and we'll see that in detail. So how do you actually build these tabular objects? Well, you can just use the Wolfram language function tabular. If you have data with a rectangular shape, you just use tabular on it, and it will generate a tabular object. So let's see that in action. Here I have a nested list, and we can see 1, 2, 3, 4, 5, 6, and there are no column names, and it's not an association here. So the rows are always numbered, and here the columns are just given numbers instead of nice labels. If you want to add some labels, well, then after your nested list, you can see here there's one nested list, and then there's another list after here, which is a list of the column names. And those are kind of like the keys in a list of associations. So now we can see that the columns have been given names. And if you already have a list of associations, Tabular will happily accept that as well. And you can see it generates the same object. There's also the function toTabular, which can be used to convert, various types of data structures you might have, again, as long as they're rectangular, into a tabular object. And more or less, at least at first glance, toTabular seems to work just like tabular. So if we provide it the same nested list, we can see that it produces the same sort of output. If we provided a list of associations with matching keys, it again produces that same sort of output. But toTabular has some extra options. One of those, for example, is that you can specify that what you're inputting here are not rows in the traditional Wolfram language sense, but columns as you might think of them and perhaps are. So here now, instead of 1, 2, 3, 4 going across that way, we have entered 1 and 2 as a column and 3 and 4 as a column. And toTabular, for reference, can also take a data set directly. So if we have this example data set we're all familiar with by now, we can see that this renders pretty similarly to how the data set looks, but this is a tabular object. And you can actually see some little hints here that these are all strings, these are all integers, and then these are booleans. And these have been automatically understood by looking at the types that are present in each column. So we have a nice efficient representation of that data set here. And just to indicate something, these are two different things. Looks like I misnamed this. Titanic data set. There we go. So here we see that the original data set is indeed a data set type. And once we use tabular on it, it has created a tabular object. So two different types of things. But you're not limited to creating tabulars kind of after the fact in a Wolfram Language notebook. You can also import things directly as tabular objects. So all you have to do in that case, say you have a CSV, in the second argument to import, you can just say tabular, and there it is, and we can run it, and it generates this nice, again, efficient tabular representation where we can see that this column is strings, and this is going to be an integer, and so on. And we could compare this to importing it as just a regular nested list here if we don't put that second argument. We can see here, it's a nested list. It's got all the same data, but it certainly isn't as nice as this lovely tabular type. And not only, do we get the benefits of having something that's totally readable just as soon as we import it, including the nice header names here, but check this out. If we check how large each of these things is in memory, we can see that the nested list is almost 3 times the size of the tabular. It's about 3 megabytes versus about 8.5 megabytes. And here, if we take a look at how long it takes to actually import these, and these aren't that big, about 28,000 entries, we'll see that it's going to take a second because I asked it to do repeated timing. We'll see that the importing here, well, in neither case is it particularly lengthy, right? We got a fast SSD here, but the tabular is, again, about 3 times more efficient. It's faster to import it. In this case, it's over 3 times more efficient, 3 times faster to import. So this disparity is only going to grow as you get larger and larger data sets. So this is a very nice little tool to have if you are indeed working with rectangular data. And speaking of working with rectangular data, well, if it's rectangular, it's 2-dimensional or rank 2, depending on how you like to think of it. So if I go to my tabular trees here, I could go to, say, the 125th row and extract the 5th column, just like normal with part, the double square brackets. And I see that it's a street. Now that all works out normally. However, if you try and extract an entire row, you'll notice that it's a little bit different. So let's just extract, say, the 437th row. We get this object called a tabular row. And this is effectively a wrapper for an association. It keeps all the column names, at least as long as you have the columns named. If you didn't have them named, you'll just get a list returned. So again, let's take a look at this. And if we click in here on this little plus sign, we can see that the columns are tree species, common name, diameter, breast height, and we can see what each type is here. And if you want to extract the actual data, you can just wrap this in normal. Remember, just like with dataset, normal is your best friend if you kind of just want to get back to the most fundamental Wolfram language expression for a thing. And if you want to extract a column, you can use the same type of syntax that we use for a regular rectangular nested list. Get all of the rows and the 5th entry, which corresponds to the 5th column. And you see this, we get a tabular column entry here, and we get the information that's relevant for the column right here. We see that it's all strings, and it's got a length of about 27,000. And if you click this, we can also see how many missing entries there are in this particular column, which is a nice thing to be able to know at a glance. And if you, again, want to get kind of the normal, most simple form of this thing, because it's just a list of values that all have the same type, you can just use normal, and you can see that street, and then there's some missings toward the end and street. So this is the normal list format that you'd expect. And you could, treat it like a normal list and get whatever part you want. Let's get the 5, 6, 7, 8th part since there's about 27,000 entries. Oh, a street. Very surprising. How do you actually work with these things? Because it's all well and good to import it and look through it and extract a row or extract a column, but how do you actually do work with them? Well, we've added a bunch of functions to Wolfram language that have the specific intent of working efficiently with tabular objects. And if you want to check those out, you can always click on this and see the tabular object guide. But we'll talk about a few of the most important functions here. Kind of your bread and butter, I would say, is transform columns. If you need to perform kind of any arbitrary operation that involves your existing columns. So if you need to transform a column that's already there into something new, you need to make some new columns using the existing columns, whatever it is, just use transform columns. So let's consider an existing tabular object. This is kind of arbitrary. It's pedagogical, right? Consider an existing tabular object that describes some lengths and widths associated with various rectangles. If you want to think about this more like a data set, you can think about it as rectangular yards. You could define that object with some random lengths and widths as follows. We're just going to make a tabular with random integers. It's going to be 20 pairs of numbers between 2 and 12, and those will be the length and the width respectively. So let's do it. There's our beautiful tabular data there, our nice rectangles that have lengths and widths. So how do we add a new property to this table? Well, like I said, you use transform columns, and all you have to do is you say transform columns, you provide it the tabular object, and then you just name your new column, and you say, okay, what's the rule for generating that new column? Take the length and take the width and multiply them together using, you can use any sort of function here. You can write a function that would multiply two inputs and you can feed them this way, but just using pure function notation is really the way to go here. And I'd recommend that you learn this if you're not yet comfortable with it. So we just do this, and when we run it, what we're doing is we're extracting each respective length and each respective width. So these are referring explicitly to the values associated with the column names here, length and width, and we're creating a new entry called area there. And as you can see, what's happened is that the length and the width have been multiplied in order to generate the area, which fills out this new column. And you can use transform columns to modify existing columns as well. And the way you do that is it's pretty much exactly the same, except instead of specifying a new column name here, you just specify an existing one. So here we're going to take length and we're going to convert it to 2 times the length. And now all the lengths have been multiplied by 2. Also notice that, like pretty much everything else except for a couple particular examples in Wolfram Language, transform columns is non-destructive. When you run this on rectangles, you are making a new copy of the tabular object with the new properties. If you did want to overwrite it, you would just say rectangles equals. And you can also do multiple transformations, including adding new columns in one function call. So let's make a transformation where we double the lengths, halve the widths, and create a new perimeter column, which is going to use the original lengths and widths since those are what exist here. If we wanted to use the new ones, we would have to call transform columns twice. No big deal, but just not what I'm doing here. So here the length goes to twice the length, the width goes to the width over 2, and I've made it numeric because since these are integers, they kind of they come out as nice fractions if you don't do that. And here the perimeter will be twice the length plus twice the width. And there we go. And there are a couple of other things to know about working with tabular objects, of course. I mean, we're just covering the basics, the most important things. But 2 of these particular functions are used within transform columns. They're column-wise value and column-wise thread. So let's see how these things work. Column-wise value lets you refer to the values of an entire column in computations on the elements of a column. And I'll clarify that with an example. So say here, I'm going to use transform columns just like usual, go to rectangles, and then for the width, I'm going to take the existing width and I'm going to subtract off the column-wise value, which is going to be the mean of the width. So I'm going across the entire column, I'm taking the mean of all the widths, and I'm subtracting the average width. So now on the widths, what I have is I've got kind of a deviation from the norm. This one is 3.35 units smaller than the average width. This one is 4.65 units larger than the average width, and so on. And if you wanted to do median here, for example, that works just the same. Any function you like. You can compute it across the whole column and then use it in a computation that affects each of the individual entries here. And here is another example where we're going to do we're going to make this rectangles tabular object. We're going to add a new column that's called really wide. It's a question. And we're just going to ask, is the width greater than the column-wise value of the mean of the width? So this will just add a new column, and here we can see whether each particular width is larger than the mean width. And you can see here that it's already automatically calculated that this ought to be a Boolean based on the results of this here, which will always return true or false. Column-wise thread is a little bit different in a subtle way, but the idea is that this will let you work with the elements from a column without needing to work with the entire column all at once. So instead of working with the whole column as one object, you can refer to kind of spans or groups of the objects in the columns. And again, I think an example will help to clarify this. So we're going to take our beloved rectangles tabular object and add a new column called running length. And we're going to thread this operation of accumulating the length as we go. And so here's the length 11, and you can see as we go, we're adding up the value at each point. That's what accumulate does, is if you feed it a list, it will accumulate everything along the way. And so this is accumulating the lengths as we go. And of course, for more examples, you can always check out the expansive documentation for all of these things. Column-wise thread, column-wise value, transform columns, they all have very good documentation like everything else. Another thing to know about, I think, is this aggregate rows. We'll move from columns to rows. And transform columns is kind of about taking an existing tabular object and performing some operation on it. Whether you're transforming existing columns, generating new columns, things like this, aggregate rows is a little bit different. So let's again learn via example. We're going to go to rectangles and we're going to take something, a property, mean length, which will be computed by taking the mean and the length, and mean width, which will compute the mean of the width. So this just computes across the entire thing one value. So we're aggregating across all of the rows one value for all of their lengths and all of their widths. And if you want to specify columns to group by before the aggregation is performed, you can just do that here in this argument. So we're going back to rectangles. We're going to get the mean width, but first we're going to group everything by length. So let's see what this generates. You can see here that all of the rectangles that have a length of 11, their mean width is 8.6. All of the rectangles that have a length of 9, their mean width is 6. So you can group up by different properties here and then compute kind of properties that are based on the groupings that you formed before. And you can see here, we group by length, but then the computation here was with width. It could be with anything, any other column if this were a more complicated data set. The point is we start by grouping with length, and then we do some sort of aggregation on the groups. And you can also just directly sort on the quote-unquote rows of this object. So if we take that object we just made and we use sort on it, note that this will just sort by the groups. Here, this order seems a little bit random. These are just the orders in which the lengths were encountered. So first was 11, and then the next novel length that was encountered was 4, and so on. And that can look a little bit weird, so you can just put a sort right in front and get a nice sorted version. And here are just some other ones that we won't cover today, but again, these are all linked, so you can check them out in the documentation. I think for people interested in kind of doing some of the stuff you might do in R, if you're moving over from R or using Wolfram Language and R, check out pivot to and pivot from columns. And maybe people who work with a lot of SQL data are also interested in that as well. So here's a little workflow example. We're going to go back to our tree data set, abandoning our lovely rectangles. How could we use these ideas that we've just now learned about in order to make a nice visualization of that data? So I'd say typically when you're working with data, it's a good idea to just take a random sample from your data and work with that. Sometimes your data, I was working with somebody recently whose data was multiple gigabytes. And when we're testing things out, we don't want to really work with gigabytes of data each time. So it's good to take a little sampling. Here we'll just take 10 trees of the 27,000. Why not? And here we go. We get 10 little data points here. And if you weren't aware, it's not the point of this class or course, but we've got a ton of geo functions. You can try running this to see all of them. But the thing I want to point out here is that the locations in this data set, we see that they're strings. These have not been, the way that they're represented in the CSV is not just as like geo positions, which is how we would represent geo position in Wolfram language. They're just strings. So we're going to have to do a little bit of computation here to get them in the format we want. And we can actually see that by using this tabular structure function. See that here, the location, it's a string. Good thing here is we've got 10 non-missing entries, everything or everywhere. So there are no missing entries, no little samples. And we got a byte count for each of these. So if we want to make a geographic visualization, which, I'm always itching to do, frankly, we're going to have to convert these strings into geoposition objects. So just like we took a random sampling of 10 before, let's just take one location and see how it is that we can actually break this up and kind of reformat it into a set of numbers that Wolfram language can use to represent a location. So just one location looks like this. Remember, this is a tabular object, so if we specify a row and a column name, we get the exact output. And you can see here that this is a string. We can use string split to break this into a list of two strings. We're going to split it on the parentheses and on the comma and space in the middle. You can see here now this is a nice Wolfram language list, but it's still a list of strings. We want to make these things numbers. We can do that with the Wolfram language function toExpression. So we're just going to put toExpression in front of this piece of code here, and you can see that we get nice numbers. And these numbers will eventually get converted into geoposition objects, but for now, let's just run this operation on the tabular object so that we've got it ready to go. So what we're going to do is we're going to go to our sample trees, we're going to transform the columns, and we're going to go to our location column, and we're going to do exactly this exact same piece of code we did up here, except instead of working on sample trees 1 location, we're just going to work on the particular location entries in the tabular. So we're going to split them up, convert them to an expression, and that's going to be our new nice location column. You can see here, now that we move over, sorry, I have my page width set a little small so that the text doesn't flow over off to the side. But if we mouse over this, you'll see that this is a location where it's a list vector of real numbers with length 2. So Tabular has computed that that's the type for this thing, and we can see that these are actual numbers here. And again, if we use tabular structure, we can see the difference. So again, the location here, we've got list, real 64, and then it's length 2. And now we can extract this data and make a nice geographic visualization. All right, named this incorrectly here. Sample trees numeric. And so we can see in this lovely vector-based geograph, we've used GeoListPlot, and we've extracted all the locations just like usual, and then we just wrap them all in geoposition. And now we can see that these are the locations of the 10 trees that we have selected. And we can do this exact same method on the full 27,000 or so entries of the tree data. So if we do this exact same thing here, the only difference is I'm putting tabular trees instead of sample trees or whatever I said. You can see that runs very quickly for 27,000 entries. We've done the conversion, and we can now just do the exact same code to visualize the whole thing. The only difference is I'm going to make the plot markers a bit smaller because otherwise they're, for 27,000 entries, there are just too many dots on the screen. You can't really make it out. And there we go. All 27,000 points visualized. And that wasn't sped up in post or anything. That really was just, computed that quickly. And you can see here for the location types that were listed, you can see why most of them were trees, right? These were trees that were, most of them were streets, rather. These were trees that were recorded as existing kind of along the streets here of Champaign, Illinois, where Wolfram Research is headquartered. Strangely enough, the parks seem not to have trees, so that wasn't in the extent of this survey, right? And you can do different types of visualizations. Again, now that we've got this lovely version of the tabular object where all the locations are stored numerically, We can put geopositions, we can do all sorts of things like compute a geohistogram where the tree's the densest. Looks like about here, about 297 were found in this location. Pretty neat. I wonder why there was no surveying here. It's an interesting thing. Maybe it's private property or something. And you can do other analyses as well, of course. So let's do an aggregate rows, for example, where we do something like compute a mean location by the number of trunks. So these different trees have different numbers of trunks. So let's group them up by their trunk number, and then we'll get the mean location on a trunk number basis. So here, wow, I didn't know it was possible for a tree to have 0 trunks. I'm not an arborist. So I don't know about these things, but all sorts of different numbers of trunks, and then they have a mean location for each of them. And if we just do this, I'm just taking that exact code there where I compute the row aggregation, and I'm using a little function here to add callouts so we can see how many trunks each one has, and voila. So here, there's probably just one trunk or one tree that had 20 trunks, whatever that means. And we can see here the mean locations for the number of trunks. And that's it for this class. So the really important things that I want you to take home after all of that are that tabular is a way that you can represent efficiently rectangular data. It's efficient both in terms of its storage size and how fast it is to do computations with. And there are a lot of different functions that allow you to conveniently operate on and transform both the rows and the columns of these tabular objects. And these new tabular objects, they fit neatly into your already existing workflows, and they take up less memory and computational time, which also does enable you, maybe you had a workflow that wasn't quite working, your data was just too big. Try it again with tabular now, and it just might work. And of course, as always, we've got some useful references here about how you can work with tabular objects, whether it's importing them, creating them, processing them, visualizing them, transforming them, whatever it might be. There's a full guide for everything.